Today we study ESA4H, a vector algebra of displacement. What we consider today is nothing but the Euclidean geometry we learned in middle school. Displacement. The displacement vector is, for example, we consider a displacement from a point A to B on a plane. And we connect the 2 points with a straight line and attach an arrow. And we say that it is a tail of an arrow and a head of an arrow. The straight path from A point to B is called a displacement vector. And a convenient way to express this displacement vector is write down two starting point and ending point, end point, and put an arrow on top of the two letters. And for simplicity, we can denote this one as some A as a bold-faced italic letter to represent a vector, or A on top of it, attach an arrow. In any case, you should specify what is the starting point and end point. And if I write in this notation, if I employ this notation, it is explicit. It is tail and head of the arrow. So if I connect 3 points, for example, A, B, and C, and I can define the addition of displacement vectors. This first one is AB arrow, and this second one is BC arrow. If I add the two vectors, these 2 points are identical to each other. The head of the first vector is identical to the tail of the second vector. Then I can combine it into a single displacement vector connecting the starting point and end point directly. So this is the addition, sum of these two displacement vectors. Okay, a zero vector. If I use the same point, the starting point and end point, they are the same. What happens? There is no change of the difference is 0. So the zero vector represents the displacement from a point to that point. So there is no displacement at all. This zero vector acts as an additive identity of algebraic property. So sum of two vectors can be defined. So this is sum of a vector and a zero vector is identical to the original vector. And because of the commutative rule satisfied by the addition of two vectors, we can say that zero vector is an additive identity. That means if I add zero vector on the left of a displacement vector or on the right of a displacement vector, the resultant vector is identical to the other vector that is added to. In a similar manner, we can extend this idea to find a solution for this equation. That means we add the two vectors and the result is 0. So what is the vector that is to be added to cancel the original vector? So because we know how to add two vectors, I have a single vector starting from A to B, and I'd like to cancel this to find out the zero vector by adding something that is to add a vector that has the same direction and magnitude. Magnitude means the length, and the direction is opposite. That opposite vector is nothing but the replacement of head and tail. So B to A. So if I add these two, A plus B and B plus A, BB are connected, the resultant vector is AA, and AA has no displacement. Therefore, the resultant vector is null vector. That is a zero vector. That is additive identity of the identity of vectors. Okay. Because it is too busy to write all the head and tail separately, usually we can use a bold-faced italic letter to represent a vector. All this small a, small b, and small c has the same tail. That is the origin. So OA, OB, OC, that can be written as A vector, B vector, and C vector. It depends. If you want to use this notation, just what you need to do is specify how these vectors are defined. So we have OA, and what is the additive inverse that is a negative of A? We know how to find the additive inverse that is to exchange the head and tail. So OA can be replaced with AO to find the negative of A vector. In a similar manner, B vector, C vector, their additive inverse can be found in such a manner. What about the difference of two vectors? Okay. Find out BC. So I can always insert the point. So this is a B and C. I can always insert a point O, for example. Then this is OB and this is OC. What should I do? To get the vector B to C using OB and OC. Now I know I can flip the direction of OB by exchanging the head and tail. That is a BO. BO is negative of OB. So if I put this one here, then resultant vector for BO and OC, BO and OC, that becomes what? The vector connecting B and C with the tail of B and with the head of C. We can make use of the previous notation definition for small a, small b, and small c. So OA is A, OB is B, and OC is a C. So using this notation, BO is negative of OB. So negative of B, that is minus B. So C minus B is identical to the vector connecting B and C with the head C and tail B. So any vector can be expressed either as a sum or difference of two vectors. Finding a parallel vector. If I have a vector, I can multiply a scalar to find a vector that is either parallel or anti-parallel to that vector. if the number, the scalar, is a positive, the resultant vector, this is a vector, and if I multiply alpha to a, and alpha is a positive, the vector is a parallel. If the magnitude of alpha is greater than 1, the length should be greater than that. Unlike mathematics, in physics, we can multiply a vector, multiply a scalar that has a definite physical dimensions. Then the exact comparison of the length is impossible. For example, I have a velocity v and mass m is to be multiplied to find the linear momentum of a particle. Then I can say these two are parallel because any particle has the positive mass, but I don't know how they are related in magnitude because a velocity and linear momentum, they are of different dimensions, so we cannot say these two are comparable. I mean, the difference is a positive, difference is negative, or difference is a zero. Only if we have some comparison with, we can compare the magnitudes of two quantities only if they are of the same physical dimensions. Next, we can consider the unit vector. What is a unit vector? A vector can be decomposed into three pieces in terms of unit Cartesian basis vectors. They are E1 hat, E2 hat, and E3 hat. They are unit vector that has a unit length, and that length means dimensionless. Although a vector, displacement vector, has a dimension of length, the unit vector is dimensionless. Hence, the components A1, A2, and A3, they are the components that has the same physical dimensions as that of the vector, displacement vector A. Anyway, the magnitude of the vector is defined by the square of A dot A. A square, vector A square, is defined by the scalar product with itself, and we know the scalar product is magnitude A dot B. For example, A dot B is magnitude multiplied by cosine theta. And because B is replaced with A, then it is cosine 0. That cosine 0 is 1. So A dot A is nothing but A1 squared, A2 squared, A3 squared. We already know that every unit Cartesian basis vector is perpendicular to the others. So A dot A has the contributions of E1 squared, E2 squared, E3 squared. That is due to the Pythagoras theorem. As a result, a vector hat that is a unit vector parallel to vector A, that is defined by a vector divided by the magnitude of that vector. The magnitude of that vector is defined like this. As a result, a hat can be expressed in three ways. They are all the same. Finding a perpendicular vector, I have a vector A that is not zero vector. Then you can find the vector perpendicular to A by solving the equation. Why? A dot B is a magnitude of A, magnitude of B multiplied by cosine. And if it is perpendicular to each other, then I can substitute half of pi for the theta, the angle between the two. then this is a 0. This is 0. If I make use of the Cartesian coordinates, scalar product of the two vectors with the Cartesian coordinates will give A1, E1, A2, E2, A3, E3, a dot, B1, E1, and so on. Only 1, 1, 2, 2, and 3, 3 components contribute to the scalar product because E1 dot E2, E2 dot E3, and E3 dot E1 all vanish. And E1 squared, E2 squared, and E3 squared are all unity. Therefore, the scalar product of A dot B can always be expressed like that. So the solution for the vector, the component, Cartesian components of vector B that is perpendicular to the vector A must satisfy this equation. If we restrict ourselves on a plane that has only two basis vectors, then it becomes quite simple. So I can say this third contribution vanishes, and this sum of these products should be 0. So if I have A vector equals A1, E1 plus A2, E2, then I can choose a vector exchanging the x and y components and then flip the sign of a 1. For example, attach negative sign on it. Scalar product will give A1, A2 minus A2, A1. So that vanishes. So you can find that exchange the x and y components and then attach a negative sign on a single component, then you will always find a vector perpendicular to a given vector on a plane. And in addition, I can multiply arbitrary non-vanishing number, scalar, to this to find a vector perpendicular to A in general. Unit circle. On a plane, I can draw a unit circle centered at the origin. In that case, the radius is defined by unity. That is unit circle. Radius is unit. If I choose the center to be at the origin, then the coordinates, x coordinate and y coordinate, must satisfy this kind of relation, cosine and sine. Because the distance between the center and a point with the Cartesian coordinates x and y must be 1. Distance is 1. So x squared plus y squared 1. We know the radius is 1. We have a right triangle. And x component here is cosine theta when angle is theta. And the y coordinate should be sine theta. Therefore, we have Pythagoras' theorem to construct a very simple relation of squared sine and cosine. We define the unit radial vector, that is the unit vector along the radius. Because the radius of this circle is unity, unit radial vector is nothing but the displacement vector connecting the origin and this point. That has x component cosine and y component sine. What about the unit tangent vector? Tangent is always perpendicular to a radius that we learned in middle school. And direction is parallel to the direction along which the angle theta increases. That is, we measure the angle from the positive x-axis and the direction is counterclockwise. We learned that a vector that is perpendicular to a vector on a plane can be obtained by exchanging two components and attach a negative sign, one of either x or y direction. We know for an angle in the region angle smaller than the right angle, the direction has the positive y components, but negative. It is going to the left, going up and going left. Therefore, the sign of y component is a positive, and the sign of x component must be negative. So I have unit tangent vector to the circle at a point with an angle of theta should be E theta hat, that magnitude is still 1, and the direction is specified with this unit vector. Scalar product. We recall the scalar product among any two between any two unique Cartesian basis vector. If the vector indices are different, they are always perpendicular to have the scalar product vanishing. And if the vector index x is for 1 is for x, 2 is for y, and 3 is for z, the squared one must be 1. As a result, the scalar product in the Cartesian coordinates becomes greatly simplified because any off-diagonal components completely vanish, and only the diagonal component, and these are all 1. As a result, our final result is very, very simple. This is one of the reasons why we use Cartesian coordinate system. It's a great achievement that they got. 6. Consider a triangle whose 3 sides are represented by A, B, and C, and sum is 0. Aha! Sum is 0. A vector, B vector, and C vector returns to the same point. So A, B, C, if I sum everything all together, the resultant vector is a 0 vector. Okay, because of this identity, I can always move one vector to the other side. So B plus C equals minus A, and A plus B equals minus C, and C plus A equals minus B, and so on. Why don't we square these both sides? Then B plus C equals minus A becomes B plus C squared equals A squared. B plus C squared is B plus C dot B plus C. And I can expand this B squared plus 2 times B dot C and C squared. We know the algebraic property, the product of two real numbers, the multiplication of two real numbers, is commutative. So I can always write it in this manner. B1A1, B2A2, and B3A3. And this is identical to B dot A. And that can be shown to be true directly using the definition of this scalar product, magnitude product, and cosine. The cosine theta, this angle is invariant on the exchange of two vectors. Okay. So using this method, I can find the scalar product of B dot C can always be expressed in terms of the linear combination of a squared, b squared, and c squared. Why don't we move this b squared and c squared to the right side and divide both sides by 2, then b dot c is 1/2 a squared minus b squared minus c squared. In a similar manner, I can make use of the other two identities and square them to find any scalar product of between AB, BC, and CA in terms of a squared, b squared, and c squared. We recall that the square of a single vector, because the angle between two vectors that they are identical is 0, cosine 0 equals 1. So a squared is the square of the absolute value. And we know the factorization formula for the square minus square is just the product of sum and difference. Using this, I can find this formula. You can make use of these relations. You can verify Heron's formula. It is very simple. 1/2 the area of a triangle. For example, this is a B and C. The angle between B and C is this, theta. Okay, what is the area of this triangle? That is 1/2 magnitude of B and magnitude of C and multiplied by sine theta. C sine theta is the height of this triangle. But we know sine theta equals 1 minus cosine squared theta, square root. Sine theta in here is a positive definite, so we do not have multiple sign in the solution. We know the cosine theta can always be expressed as a b dot c divided by magnitude of b and magnitude of c because of the definition of the scalar product. If I substitute this, and then we can expand this. A little bit tedious, but it is straightforward to find out Heron's formula. You know, many people think that Heron is a mathematician, but he was a physicist when physics was not discovered, and he developed a very interesting steam engine. That's it for today. Thank you.